is Monica Gupta. I'm a technical lead at Intel working in a team whose mission is to ensure Intel architecture works best on Windows and Windows runs best on Intel architecture. As part of my role, I get immense pleasure of collaborating with our great partners Microsoft. Nothing is constant in my job. Hardware keeps evolving, software keeps changing, and to ensure that they both work in unison, they both work best together, we have to keep innovating. It is really gratifying to see the benefits of all the work my team, myself, in deep collaboration with Microsoft have achieved over the years. Today, we are going to focus on Alderlake's new hybrid architecture, Windows enabling that was done to maximize the usage of this new architecture, and what are the key practices software ecosystem could leverage to take the benefit of this new technology. Hybrid architecture integrated two core families, P-cores and E-cores. P-cores are optimized for performance, and E-cores, while they provide reasonable performance, they are highly optimized to provide an efficient system. Some workloads really need the performance of P-cores. For example, you're playing a game or doing some AI operations. But some applications scale really well with the addition of E-cores. Did you know Intel could add 4 E-cores in approximately the same area as one P-core, providing us with a really efficient system? Processor capabilities are dynamic in nature. Intel's hybrid technology provides processors' performance and efficiency capability to Windows and notifies Windows whenever there's a meaningful change in these capabilities. This technology is also available and works well with Windows 10. Intel's Thread Director technology analyzes thread behavior in terms of instructions that the thread is executing and provides per thread performance and efficiency classification back to Windows in order for Windows to identify the threads that could really gain maximum performance from P-cores versus E-cores. Windows, with its inherent and evolving information about software thread needs and system goals, is in an amazing position to place the right thread on the right core. Let's look at some examples to understand this further. The Thread Director technology classifies threads into different performance and efficiency classes. On this example, you can see there are a number of threads in different classes that are ready to run. Say there is no contention for those P-cores or performant cores, and as threads are demand-oriented, Windows would place those threads on the P-cores or the most performant cores. Now let's say the contention between the performant core increases. In this situation, Windows would move those class 3 threads from P-cores to E-cores, or it would schedule them on E-cores based on the way the threads came in. So if a class 3 thread came in later, it would be scheduled on the E-core. And how did it decide to move that class 3 thread to E-core? That is based off Intel's Thread Director technology, which classifies that class 3 thread might not be able to gain as much performance from P-core versus E-cores compared to other class of threads. Over time, if the processor capabilities change, and if a particular class thread could gain more performance from E-core versus P-core, then Thread Director would enumerate that information back to Windows, and Windows would move that class thread on the E-cores. Foreground and background is only one of the characteristics that influences quality of service needs of different threads. Let's now deep dive into what are the various characteristics that could influence this cost level of a thread. What better than to hear from an expert? Today, I have the honor of inviting Tristan Brown to walk us through what are the various quality of service levels of a thread and what are the various OS APIs that application developers could leverage? What are the various frameworks that software ecosystem could leverage to better influence this identification in Windows? I've been working with Tristan for over 8 years now on different innovation and enabling to bring about Intel and Windows processor power management technologies to life. Here you go, Tristan.
Thanks, Monica. My team has been working with Intel for over 4 years, developing Windows support for the Intel hybrid architecture, and I'm excited to share a few tips on how developers can make their software work better with Windows 11 on Alderlake. Windows categorizes process and threads based on user experience expectations into different quality levels. The foreground application the user is interacting with runs at the highest quality of service, and hidden or minimized applications run at a reduced quality of service. For system services and kernel threads, Windows uses work on behalf relationships such as RPC calls and other heuristics to infer the quality of service requirements for individual threads and to make sure threads contributing to the end user experience are categorized appropriately. Quality of service hints have been used by Windows to control performance and efficiency trade-offs on threads for several processor generations. On Alderlake systems, Windows uses both quality of service and thread director to additionally determine which threads should be prioritized on P cores to maximize end user benefit, and which threads can be run efficiently on E cores without impact. Applications can help Windows make informed decisions by opting in or out of power throttling. Opting into power throttling provides a hint that your application is performing work that is not performance sensitive, and Windows prioritizes running work efficiently to leave more headroom for higher quality of service work or to improve battery life. Applications running background maintenance tasks are good candidates for opting into power throttling. For example, content indexing tools, online backup, background software updaters. Applications can also opt individual threads into power throttling if they have background work running in the same process as their user interface. Threads which contribute to user business, such as UI threads or real-time virus scanner threads, are not good candidates for opting into power throttling. Applications can opt out of power throttling to run at a higher quality of service level. Applications should use the power throttling opt-out sparingly, as doing so will have a battery life impact and can take power budget away from other applications the user is interacting with. Windows is generally cautious about assigning reduced quality of service, and most applications should not need to opt out. Note that opting into or out of power throttling will not always make your application run on an E or P core. Windows will take additional considerations into account, including whether or not the system is running on battery and thread director hints to decide which type of core will be most performant or efficient for an individual thread. Opting in or out of power throttling is simple with the set process information and set thread information APIs. Set the control bit for execution speed to indicate the application wants to control power throttling. Setting the state bit opts in and clearing the state bit opts out. Clearing the control bit will return control back to Windows. Note that while opting into execution speed throttling may reduce CPU performance while your work is running, that isn't guaranteed. Windows does not use a one-size-fits-all approach to manage quality of service expectations. On a thin and light laptop running on battery power, Windows will likely limit execution speed of power throttled threads. On a desktop workstation, power throttling may only be used to help prioritize which threads get P cores when the system is heavily loaded with more active threads than P cores. Microsoft and Intel work closely with each other and our OEM partners to tune the scheduler and power managers' behavior for different types of systems under different operating conditions. End users can also influence this behavior by configuring the system's power mode in the Settings app. By opting into power throttling, applications can better tailor the behavior to the end user's preferences. Windows provides APIs for applications and drivers to directly control thread affinity. These APIs should be avoided where possible. If an application wants its threads to run most performant or efficient, it should instead use the power throttling hints to bias execution towards P or E cores. Note again, Windows and Thread Director will work together to determine which core will be the most performant or efficient for an individual thread. Your application won't always get the best results by directly setting thread affinity to P or E cores. If an application needs to guarantee 2 threads run on the same processor, or 2 threads run on 2 different processors, it can use the CPU sets APIs to do so. These APIs are designed to work better with heterogeneous scheduling. The CPU sets API allows applications to enumerate distinct CPU sets and associate a process or thread with one or more CPU sets. Get system CPU set information lists all the CPU sets on the system, including a variety of characteristics applications can use to determine the properties of each CPU set. Set thread selected CPU sets indicates which CPU sets an individual thread should run on, and set process default CPU sets indicates which CPU sets should be used for threads without explicit configuration. In this example, the process is using 2 CPU sets to isolate all other threads in the process from running on the same core as the current thread. Applications should use the CPU sets API only when necessary to give the scheduler the most flexibility in determining which threads are allowed to run on each core type. Windows built-in multimedia APIs, such as Media Foundation, provide additional quality of service hints to improve efficiency and performance on hybrid platforms. Media playback workloads understand their deadlines, for example, for decoding a frame of video, and can batch decode multiple frames of video ahead of time. Windows uses this information to schedule batch workloads on E cores, prioritizing efficiency to increase battery life and to keep power budget available for other application threads. Normally slow and steady is more than enough to complete media work in time. But in the rare case a deadline is close to being missed, Windows will automatically raise quality of service for that task and boost up to high performance on a P core, preventing the user from observing a dropped flame or audio glitch. To take advantage of this advanced scheduling, applications should make use of Windows built-in frameworks and controls for media playback, such as Media Foundation or the Windows.media namespace for UWP apps. While most of these tips apply to application developers, driver authors also play a part in ensuring that users get the best experience on hybrid platforms. Drivers should avoid the use of affinity for threads and DPCs. Drivers can also opt their threads in and out of power throttling by using the ZW Set Information Thread API. Drivers without per-processor queues should also configure IRQ policy to work well with interrupt steering. Interrupt steering configures driver interrupts based on overall system demand to either spread out across multiple cores or consolidate down to fewer cores. Interrupt steering works hand in hand with the scheduler to make sure that cores processing interrupts are also able to run threads readied by those interrupts. If your driver configures interrupts to run on a specific core, and Windows and Thread Director have decided not to use that core for the current workload, this can lead to both performance and efficiency degradation. Performance degradation due to the latency of waking up a second core to run a thread resulting from that interrupt, and efficiency degradation due to the fact that 2 cores need to be woken up while servicing the interrupt instead of just one. Configuring your driver to work well with interrupt steering is as simple as leaving IRQ policy set to machine default. This is the default configuration for both WDF and WDM drivers, so driver authors don't need to do anything extra to get the benefits of interrupt steering. These best practices will help your applications get the most out of Windows 11 on Alderlake. They're also beneficial in systems running Windows 10, and on systems using homogeneous processors. So you should incorporate them in your application regardless of which version of Windows or which processor your application is running on. Back to you, Monica.
Thank you, Tristan. This is really exciting, and it is great to learn how Windows identifies quality of service needs of different threads and provides powerful tools like power throttling APIs and Windows Media Framework for software ecosystem to influence that identification. How avoiding affinity and leveraging the default interrupt steering policy can ensure applications and drivers can take maximum advantage of the inbuilt smart scheduling and interrupt steering. We look forward to seeing software ecosystem leveraging these tips on hybrid system to unleash the full potential of Windows 11 OS and Intel's new Thread Director technology. Thank you.